MPLS is mostly seen inside the provider's network, between this border to that border. We have MPLS. To connect between service providers, we have BGP. So you will see BGP and MPLS in the web. So the edge device of an enterprises will not be aware of any MPLS labels. Only between the provider edge to provider edge, you will see MPLS deployed, MPLS in use. Now let us see how MPLS can quicken the routing process. How a label switching will be more faster than IP routing. In our introduction to MPLS, we learned that there are labels involved, and this label makes the forwarding decision faster. How? I told you in the previous class, when a packet arrives, it comes with a label. The router that receives this packet only looks into the label and decides the exit interface and the gateway. Exit interface and the next hop, just by looking into a label. But first of all, how the sending router knows the label that it has to put so that the receiver will know the destination. Let me make it clear. We have router 1, 2, 3, 4. Let's say, for example, we got 4.4.4.4 advertised by OSPF, and router 1 learns 4.4.4.4 in its routing table. According to router 1, it has to send to router 2, and likewise so according to router 4, it is directly connected via G0, router 4, router 3, router 2. So the routing table shows the next hop. Not only that, it will show you the exit interface. Let's say G0 everywhere. G0 and the gateway is R2. This is what we will have in routing table usually. Even now, even after enabling MPLS, there is no change in the routing table. There is no change. All right. Now, where is the change? The change happens in two places. One, the packet. Two, the CEF table. You know, in R1, R2, R3, we will have a CEF table 4.4.4.4/32, exit interface via G0, and the gateway is, let's say, 10.12.0.2. This is what we used to have in our CEF table in R1. Likewise, in R2 and R3. CEF stands for Cisco Express Forwarding, which is a forwarding table in a layer 2 buffer. The advantage of using Ceph is the packets need not to go through the layer 3 route lookup every time. Just by looking into this layer 2 buffer, layer 2 table called Ceph table, it will be in a position to decide the exit interface and the gateway. Usually why you go to routing table? To know the exit interface and the gateway. If those informations are available in layer 2 itself, then there is no necessity for a router to look into the routing table layer 3 engine for any decision. Whether you enable MPLS or not, the Ceph is enabled on every router. Packets move using this Ceph every hop. Now, why I am bringing Ceph in MPLS topic? The reason why is Ceph is already making your routing faster. If you want to make it much more faster, you need to do some more refinement to the Ceph table. Yes, that's what MPLS do. For every network in the routing table, see, I have just taken only one network as an example, 4.4.4.4. For every router, for every routes in the routing table, for every route that is seen in the routing table, a label is generated dynamically, and that label is assigned to the Ceph table. Understand this. Labels are assigned to the Ceph table, not to the routing table. So again, you don't need to do a layer 3 lookup on the router. For example, label that is generated locally for 4444 is, I'm writing here 34, 22, 16, 3. Labels are always from 15 onwards. But this 3 is for a purpose. We call it as PHP. I'll talk about that later. Other than the originating router, see 444 is originating from where? R4. Other than this router from where the network is originating, rest of the routers will generate a label. That label will be greater than 15, and the maximum is 65535. Because 16 bit is 20 bit is given for MPLS label, not 65535. It is more than that. 2 to the power of 20. That many labels you can have. Two to the two raised to 20. So these many labels you can have. 20 bit is for MPLS label. You remember that is how we finished our previous session. Out of 32 first, 20 bit is for label. So label starting from 15 can go up to this big number. Now, for example, I have taken 34 is the label generated by R1 for 4.4.4.4. 22 is the label generated by R2 for 4.4.4.4. And 16 is the label generated by R3 for 4.4.4.4. As I said, other than the router from where the network originates, they will generate from label 16 onwards. So the only router that can use label number 3 is the originator. That 3 actually tells the receiving router, in who is the receiving router, what it is receiving. See, there's labels that they generate, they don't keep it for themselves. They advertise it so that others can use. Otherwise, why you need label? The example that I gave you, no, for your baggage when you check in, they put a label behind the ticket. See, they give you the label. They want to use that label, that particular label number, that particular barcode with label number for your baggage to be handled properly. Why they are giving you? So that you can claim your baggage when you want. See, if they don't give you that label, if they don't advertise the label, if they keep it for themselves, it is no use of having that label, isn't it? So the label that is generated needs to be given to the other routers so that they can use it. So router 4 generates label number 3 because router 4 is the originator of this 4.4.4.4. To tell router 3 to tell to the next router that I am the owner of this 4.4.4.4, it uses this number, it uses this reserved label number 3. The reserved label number 3 is to simply tell that I'm the owner of this network. You are receiving from the originator. You are receiving from the ultimate router. It's me. If you are sending any packet to 4.4.4.4, I am the ultimate router. I am having that network 4444. Therefore, just want to inform that it's me, the ultimate router for this destination. I'm the origin. In another word, I'm the originator of this network. I'm advertising you. When you reach me, you need to know that I am the ultimate router. There is no more hops. R4 is telling that there is no more hops. I am the last hop. To whom it is telling? To the next router. So that R3, when it sends the packet to R4, it will know that I'm sending to the final hop. Final hop to reach this destination 4444. That is the message label number 3 conveys. Fine. Why it has to convey this? We'll come to that portion later. But now, labels are advertised. That is one important point that you have learned today so far. The reason for labels advertised is if anyone wants to send traffic to 4444 to router 2, okay, let's take like this. A packet is coming from somewhere. Let's say source is somewhere 1.1.1.1. It is somewhere behind R1. Don't think it as it is coming originally from R1. The packet is coming from somewhere, from the customer, and assume R1 is the provider edge where the Mpls starts, and the destination of the packet is 4.4.4.4. As the packet enters into this Mpls running router, this is the very first router in the topology where the Mpls begins. We call it as in-grease router. That's the English word, in-grease. Ingres for MPLS. And R4 is considered as egress router. Now in the ingres router, what will happen, as soon as the R1 finds by going through the big layer 3 header, hope you remember what I told you in the previous class. The layer 3 IPv4 header will have too many fields, not just the destination IP. It will have protocol, version, checksum, fragment, option bit, source IP address bit, field, destination IP address field, TOS field, and much more. After reading all the layer 3 fields of the incoming packet, it knows one thing, that I have to forward this packet to 4.4.4.4. So it looks into the Ceph table. How shall I go to 4444? Router 1 says you need to exit via this interface and you need to go to this gateway, and the label is 22. This is the important place. The Ceph now, after you enable MPLS, got a new field called label. So now when this packet which was simply an IP packet now comes to router 2 with a label called 22. How router 1 knows that I need to put 22 before sending to router 2? Before sending to this gateway, can someone tell me how router 1 knows I need to put 22 label?
R2 had already shared it with R1?
Correct. Advertisement. So as I told you earlier, every router advertises the label that they have decided to use for each network in the routing table. So through advertisement, R1 knows that if I put 22 label, R2 will understand where I am willing to go. See, according to R2, I told you the label 22 means 44. So when router 2 receives the packet with label 22, it understands, I know where it has to go. So again, it is going to push by swapping with the label number 16. So now it deletes the 22 and puts label number 16. That is what it is seeing in the Ceph table of R2. The Ceph table of R2, label number 16 will be seen, which was advertised earlier by R3. So it puts label number 16 and sends to R3. Look at this. This router 2 has not done any route lookup. The packet was coming with the label number 22. When it receives packet with label number 22, it knows that the label 16 is what given by router 3 for the same network which I am considering as 22 label. We call it as LDP binding table. So what R2 will say, R2 will have an Mpls LDP binding table saying for 4444, my local label is what? 22. My neighbor label given by R3 is 16. It will maintain this table, the Mpls control plane called binding table. So what R2 does is it simply takes the 22 out and puts label number 16 and send it to router 3. See, two things you need to understand here. One, R2 did not read your layer 3 header of the incoming packet. It was just reading this portion of the packet. It did not read this portion at all. Which one? R2. It just read the 22 and understand that I need to swap with 16 and send it to R3. So it just swapped with 16 and sent to R3. And an R3 receives it, and R3 knows that when my local label is 16, R4 given label for that same network is 3. So even R3 don't do any routing table lookup. Two things they don't do. One, they don't read the layer 3 header of the incoming packet. Number two, they don't look into the routing table. Even before MPLS, routers were not looking into routing table. It was only looking into Ceph table. Now the same Ceph table has also got the label to reach the next router. So on R3 to reach R4, what will be the label? 3. On R2 to reach 4.4.4.4, what will be the label on Ceph table? So can someone answer me? I'm repeating the question. On R2, when a packet is received with the label number 22.
16.
Correct. R2 Ceph table will have the label given by R3, not given by R1. See, you know one thing, for you not to have confusion, I did not write one point here. Meaning not only local label and R3 given label, you will also have R1 given label. But R1 given label is useless. Why? It is going towards the downstream. Even though you have it in the control plane, it is of no use. Advertisement will come from all direction for all the network. The binding table will maintain it, but only the downstream towards the destination, the Ceph table has got the entry. So labels will be only as per the Ceph table. Will Ceph table show you this direction for 44444? No. So R1's label, even though R2 knows that R1 uses 34 as a label, R2 won't use it to encapsulate because R1 is not the direction to reach 44444. Okay, that's the reason why we need Ceph table here. Otherwise, you can simply use that MPLS table, swap 22, 16 and go, no? But why you need Ceph table? To determine the direction. Ceph table will have the routes pointing towards the right direction, not to the backward, not to the upstream. Fine. So now we understood how MPLS labels reduces the time taken to process. They don't do two things. They don't look into the routing table. They don't read the layer 3 header, but still they can take the routing decision. But still they know where to forward, via which interface to send it out. Fine. What is next? Why do we need that label? Yes, please. Question.
Quick question. So the Ceph table also includes like say the label and then the label associated with forwarding the packet also. Like say for example, on R2 you receive a route with a label 22, and then there is an LDP table also which tells the router whether the label 22 needs to be forwarded to the router with label 16. So I presume the LDP lookup doesn't happen. That information is already there in the Ceph table. Like say for example, there is no LDP table lookup also. Basically, the prefix also has 22 and 16 associated with it on the Ceph table. Is that correct, or is that?
No. I'll repeat again. R2 Ceph table will not have label number 22. R2 Ceph table will not have label number 22. R2's forwarding database will have 22 and 16. R2's forwarding database, Mpls forwarding database, which our Gaurav was mentioning, like LDP database, LDP forwarding table, will have both incoming label, which is 22. Incoming label is nothing but a local label. R1 is sending 22 as a label. That is what coming in. R2's local label is what incoming label to R2. And the outgoing label will be the label given by R3. Now, how this forwarding table is built using this Ceph entry. Why the forwarding table is not having label 34 on R2 as an outgoing? Why R2 is not having 34 label as an outgoing? Because R1 is not the direction to reach 44444. How R2 knows that? Ceph table. Ceph table has clearly told the direction. This is the direction you need to go. So this label 22 is what going to be copied to the forwarding database, Mpls LDP forwarding database table. So forwarding table will be definitely looked up. But why I did not mention about forwarding table, because one thing is I have not spoken so far about LDP. Second is I'm trying to explain you how the routing table is replaced. How a layer 3 lookup is replaced. For that I have to bring Ceph in picture. So how layer 3 lookup is avoided? Because you got the routing decision, the routing database in a layer 2 level called Ceph. So Ceph is equal to the routing table rib. That is how you know the direction. You don't need to look into the routing table for the direction. You have the Ceph. So that same Ceph table also shows you the exit label. After this only comes that forwarding database. Forwarding database, Mpls LDP forwarding database gets an idea of what can be our exit label only from Ceph. Is that clear?
Yes. So this Ceph table will also have the 22 and 16 on the same entry?
No. Again, I'm repeating. Ceph will not have 22. Ceph will have only 16. Because Ceph table's job is not to talk about incoming. Routing table's job is to show you the next hop. Ceph table is also a kind of routing table in a layer 2 level. Why will it have label number 22? It won't have. It will have only label number 16. Ceph table after Mpls, the Ceph table will have only the outgoing label, which is the label given by R3. But there is another table called forwarding database, Mpls forwarding database. That table only will have local label 22, outgoing label, no, first thing is the destination network, local label, outgoing label. What is that? 16. I'm writing for router 2. 16. And then the gateway. Let's say the gateway is 10.23.0.3. Now before that, packet sent, packet received, and the gateway 10.23.0.3, which is router 3's address, and the interface, let's say G0. This interface, this gateway, label given by router 3, local label. And this will show you how many bits of packet we're using this label, how many bits of packets, how many bits of data has used the service, label service. This is for troubleshooting, if the bits are increasing, which means they are using label. If they don't, then you have some problem with MPLS. Anyway, let's not get into the troubleshooting. Now, these are the informations that you will have in a table called Mpls forwarding database. Mpls forwarding table. Now, going back to this label number 3. What is special in label number 3? As I already told us, as we already know, router 4 tells that I'm the last hop. So while advertising, R4 uses this label 3, and when R3 receives, it understands that I have to pop the label. Pop the label, meaning I should not put label and send the packet here. Why? Let us assume instead of 3, it is giving 33. What you will do? You will put label number 33 and send the packet. Packet will be received here. But when you look into the Ceph table, will there be any entry? No, because it is directly connected. Will there be any other label given by anyone else for this 44444? No. So what it will do? Oh, there is no label. Then let me now go through the layer 3 header. Layer 3 header, layer 3 header. I don't know what is this label number 33. What is there in the destination field? Let me find. And it will start reading all the field of the layer 3 header. Then it understands, aha, destination IP address is 4.4.4.4. Okay, now let me look into the Ceph table for 4444. And Ceph table says, this is the interface. So 2 times you have to do lookup on the incoming packet. First you did MPLS lookup and then you did IP lookup. To avoid this, we have that label number 3. When router 4 advertises label number 3 to router 3, router 3 when it is advertising this packet, it will advertise without any label. Sorry, when it forwards the packet, when R3 forwards the packet, it will forward without any label so that R4 can read the layer 3 header and decide the exit. There is no need for Mpls lookup and then a layer 3 lookup. How R3 knows that I should not put any label before sending to R4? Because R4 has signaled R3 saying, don't send any label to me because I am the last router, you know. If you send with the label, then I won't have any other label as outgoing for that network. It will become a double job for me. I have to now look into your layer 3 header and then decide on the exit. So better do not send any label to me. Just send it as an IP packet. I'll take care of it. This is what the meaning of label number 3. Label number 3 makes R3 understand I should not put any label before sending to R4, which reduces double lookup, Mpls lookup and IP lookup into single lookup, simply IP lookup. We call this as PHP, penultimate hop popping. Penultimate, see how nicely they have named it. Penultimate hop popping. Pop the label, pen it, write it down. That's the meaning. Write it down that there is no need of label for this before going to the ultimate hop. Pen it, write it down. So router 3 writes it in its memory. Oh, I should not put any label if I am sending to R4 for this destination. Write 1,000 times till you get it. Okay, it writes 1,000 times in its memory. I'm just joking. So it writes in its memory that I should not put label while I'm sending to R4 if the destination is 44444. See how easy it is to signal with a reserved label. R4 has signaled R3 with a reserved label that reduces double lookup into single lookup in R4. We call it as PHP, penultimate hop popping. Fine. Earlier I was telling you that the labels are generated on every router and the labels are advertised to the established neighbors. How the neighbors are established? MPLS uses multicast and MPLS uses UDP by using a protocol called LDP. LDP is what called as label distribution protocol that helps to distribute the label. This LDP will use UDP 646 port number and do multicast because they don't know the neighbor, no? They don't know each other. Initially, it will do UDP multicasting and they first discover the neighbor. After discovering the neighbor, it turns to TCP. And now once the neighbor is established, the updates are shared with the label. So label distribution protocol is involved in discovering the neighbor. What neighbor? MPLS LDP neighbor. Only to those neighbors with which the neighborship is established using TCP, using point-to-point, using one-to-one relationship, not multicasting, unicast. The labels are advertised for the prefixes. So for every prefix, on R4, label will be advertised. Likewise, every prefix on R3, label will be advertised. They generate label not only for one network. Now I've just taken one network for as an example. You may have 1,000 network. Why 1 million network? For each, you will have label dedicated, unique. And the labels are distributed using LDP. Cisco also got another protocol to distribute the label, which is TDP, Tag Distribution Protocol. But the tag distribution protocol varies in this. What? TDP uses always UDP. 711 is the port number dedicated for TDP. Always. So we have learned the two protocols to distribute the label. One is LDP, which uses UDP in the initial stage. After forming neighbor, it switches to TCP, and same port number for both UDP and TCP, 646. LDP is a protocol, TDP is another protocol that you may use it if you want. This is a Cisco's protocol. So if you're having all the routers Cisco, or at least, if you're enabling TDP here, this should be Cisco device. If this is a non-Cisco device, then you may have LDP this side. No problem. One direction TDP, one direction LDP. Nothing wrong. So here also you need to have LDP. And here you may have again TDP. This is the only non-Cisco router. So this is all Cisco, let's say. So Cisco routers runs TDP. Non-Cisco, they know only LDP. Other than that, there is nothing big wrong in it. In enabling TDP. TDP is equally good as LDP, except this thing called UDP. TDP uses always UDP, whereas LDP can use TCP. Both does the same job, distributing the label with the prefix. So here we have learned the logic behind label switching. And we understood the protocols involved in distributing the label. In Cisco, when you enable MPLS, LDP gets default enabled by default. Do not expect this luxury in configuring MPLS with other vendor devices like Alcatel-Lucent or Juniper or other routers. It is not that easy. But concept is same, but you have to enable TDP as a protocol separately after enabling MPLS. You have to enable MPLS and then you need to enable LDP separately. Whereas in Cisco, seamlessly LDP gets enabled when you enable MPLS. Only on the show commands you will use some LDP. You will never configure LDP because it gets enabled when you enable MPLS. Enabling MPLS is very simple command. Globally, to enable MPLS on the router, meaning to enable the feature MPLS, you need to just go to the configuration mode of a router and type MPLS IP. That's all. But this will not run MPLS on the interface. You must also enable MPLS on the interface level. This is just to kickstart that process, that feature called MPLS. So after this, you have to go to those service provider facing interface. Let's say interface G1 is facing customer. Don't go there. Customer facing interface, you should not run MPLS. So go to the interface that is facing the service provider, meaning in our topology, don't go to G1, only on G0, because G1 is facing customer. You don't run MPLS through the customer. So on G1 interface, repeat the same command. Now MPLS is running on this interface only. Globally, the feature is enabled, but not running on all interface. It is running only on this interface. You don't need to wait for me to do a demo on this. You can try at your home. Take like this for router and configure loopback interface on every router, configure network between the routers, enable a routing protocol, preferably OSPF. It is good to use link state routing protocol when you are doing any MPLS related lab. A link state routing protocol is what recommended. You will know why later when we go to layer 3 VPNs and so on. Now, after you enable MPLS, see MPLS, enabling MPLS is only this much. You need to verify, right? So use these commands that I'm showing you. Show MPLS LDP neighbor. Whether you use LDP or TDP, that doesn't matter. This is the only command. Boom, boom. This is the only command, even if you use TDP. This will show you the MPLS LDP neighbors. Next. If you don't see your neighbor, then you need to troubleshoot, right? Check whether the interface is running MPLS. Show MPLS interfaces, LDP interfaces. And if you find MPLS, then you should see neighbor. But I'm not seeing neighbor. What may be the reason? Listen. I enabled MPLS on this interface, this port. On this interface, this port. I enabled the feature MPLS on both R1 and R2. But still I am not seeing neighbor. So I went and checked the interfaces by typing this command show MPLS LDP interface. It shows that I am running MPLS on G0 on both the router. But still I am not seeing neighbor. What may be the reason? The only reason is this. There are many reasons. The silly reason is you did not say no shutdown here or here. The other silly reason is you might have not given IP errors in any one of this port. But the important reason is, if you have not done that silly mistake, the important reason is, if you are using loopback, this address will be taken as the router ID. Like OSPF, MPLS will also take this address as the router ID. And this router ID, if it is not reachable, MPLS cannot form neighbor. If it is not reachable, MPLS cannot form neighbor. R2 will say, I am 2222 speaking to you by taking this as router ID. But R1 will say, who are you 2222? Batanai. I don't know who you are. I don't know who you are. What you are speaking. Because there is no route to reach 2222 in the routing table. So make sure you run OSPF on this loopback interface also, so that the router ID of R2 will be reachable from R1 and vice versa. That will be the major mistake why the neighborship has not come. Next. Show MPLS binding table. This will show you the local label. If you are in router 2, it will show you the local label of R2, label given by R1, label given by R3. Next, show MPLS LDP. No LDP will come. Show MPLS forwarding table. It will show you, as I said earlier on the top, it will show you all this information. At last, show IP ceph 4/4/4/4/32. It will show you the ceph entry along with the label, something like this. Right? If you do these things, you will understand all that we learned. If you use the show commands and verify, you will understand all that I have delivered to you today. Anyhow, I'm going to do this demo tomorrow. No class. But I encourage you, it's not a difficult thing. You need a topology, and you need to just put this command on the global as well as on the interfaces. Right, and then verify. When you ping and then type this command, you will see number of bits that have used this label service, the forwarding table. Any question?
So this requires the routing protocol in the to work basically between the routers. So there has to be a established reachability between all nodes for MPLS to work on top of it. Is that?
Come again.
So,
You need a routing table, a routing protocol to provide you the route information in the routing table. Because the labels are going to be assigned only to the prefix. MPLS job is not to discover routes. MPLS job is to assign labels to those routes that are already there in the routing table. If your routing protocol is slower, your routing table convergence will be slower. So there is no point of having MPLS. So we also need to have a fast routing protocol. That's why I prefer link state routing protocol, OSPF.
Okay. Okay.
Any other question from others?
No, sir. I'm good.
All right. So